Hello everyone, to lecture 6. As always, some announcements. I'm going to do these in different order than I put them up there. Homework 1, that's due tomorrow. Hopefully you've started on it by now. You definitely want to start on it today if you haven't, because you are slightly constrained by the office hour schedule in case you get stuck or if you run out of attempts. That's where you have to go to get and reset. There aren't going to be any exceptions to that rule, so you definitely want to start now if you haven't already. Homework 2, which is on games, yesterday's and today's material and lecture will be released later today. And Project 2, which is a project that is based on the same material, game playing against an adversary, will be released later today, possibly tomorrow morning, but between now and next lecture. I talked about the mini contest that we just released for search, where you're racing to pick up all the pellets on the other side of the board. As soon as that one closes, and we announce the results from that, we're going to launch the second mini contest, which is based on the adversarial material, because then rather than just racing to pick up all the pellets, there's also an element of defense, where you can send your Pac-Man to the other side and pick up dots, or stay on your side and it turns into a ghost and you can eat Pac-Men that are trying to get your dots. It's pretty fun. So there will be another announcement about that much later, maybe not much later, next week when it's closer to release, but just something to keep in mind when you're implementing things for the project. This might not be the last time you see this code if you want to do something for the contest, so maybe write some clean code or something. Yeah. Last point, section attendance. Attendance to all of them has been pretty reasonable, although not surprisingly, the sections that are close in time to lecture, right before and right after, are much more crowded than the other ones. So if you're not super time constrained and you'd like a little bit more individual attention or to work in a smaller group, the 12 to 1 on Tuesday, Thursday, and evening 6 to 7 Monday, Wednesday sections, I think had less than 10 people, around that number. So yeah, if that's something you're able to do, that might be a worthwhile thing to try. Questions about logistics? Yeah.
We don't have class on Monday.
Yeah, good point. That should probably be an announcement. There's no class next Monday for the holiday, 4th of July. So lecture starts next Tuesday, next week. No Monday lecture. Thank you. Or section or anything. Everything's canceled Monday. Okay, so today, as hinted at yesterday, we're talking about uncertainty and utilities. So we already saw yesterday a certain form of uncertainty where we don't have total control over what's going to happen to the environment after we take an action. But there we did it in an adversarial context where we take an action and then it's our opponent's turn, and they take an action, and they do whatever they can that's worst for us. Now we're going to talk about uncertain in the random sense. So now, rather than the opponent taking whatever move is worst possible for us, we have some probability distribution over how likely we think it is for them to take each move. So we saw this slide yesterday, talking about the worst case versus the average case. And as a quick recap of what's going on here, we are trying to maximize the utility at the leaf that we end up at. And we would really like to get this 100. It's much bigger than anything else in the tree. But if we're playing against a perfect adversary who's minimizing our score, remember zero-sum game means they're maximizing their own score, but it's the negation of our score, so we just model it as them trying to minimize our score. There's no way that if we took this move to go down this branch, we'd get here because we know that the minimizing player would choose this move and we'd get 9, which makes this the better move. That's when we're playing against this guy, the perfect omega robot who knows how to play tic-tac-toe. But we also saw that sometimes the opponent is not perfect at the game, and we might want to model that the opponent might sometimes make a mistake, or even more explicitly, we might have an opponent that is literally performing some random event, like rolling dice to decide where to move, something like that. So today we're going to talk about changing these min nodes to chance nodes. And that does exactly what I was talking about, where instead of just choosing the minimum of all successors, it takes the expectation according to some probability distribution over how likely it is that that agent will take each action. So that's going to be called Expectimax Search, and it's really not all that different from what we were doing with Minimax. You might be wondering, I did go through a couple examples, why would randomness be a good model for the opponent's action? Well, explicit randomness, rolling dice, unpredictable opponents like the ghosts moving randomly, or more generally, having opponents that, for some reason, some information that we have leads us to believe that they are not going to play optimally. Sometimes they aren't going to see the best move, and so we try to estimate how they're going to play, simulate their choices, rather than playing perfectly, as maybe 80% of the time they're going to make their best move, and the rest of the time they'll choose their second best move, something like that. These are all different examples of scenarios where we can apply Expectimax. And then another one where it's a little bit of a strange model at first to think about calling it a multi-agent game, but there's randomness in real-world tasks for robots where if you're trying to move over to the other side of the room, the wheels might slip. If you're trying to turn a motor to move an arm, the motor might fail. All sorts of contingencies that are random events in the environment, we can model them as another agent that is taking a random move according to some distribution. So now, values, remember yesterday, it was the maximum possible utility that we can guarantee we can get. Now the value of a state is the maximum expected utility that we can expect to get, or that we can guarantee that we'll get on expectation. So now when we're propagating values up these trees, what we end up with at the top does not necessarily have to be the utility at some leaf at the bottom. It can be some weighted sum over all of them. And we have Expectimax Search, which is this algorithm. Max nodes exactly the same as yesterday. Choose the max of all your children according to the Expectimax value. But chance nodes, no min, take an expected value. And we'll do a quick refresher on what expected value is in a minute. Yeah, later, I think this is actually, yeah, this is tomorrow. We're moving super fast this summer. We'll talk about Markov decision processes, which is the framework we use for this kind of environment when we want to do reinforcement learning. So perform a task a bunch of times where we start out not knowing anything about the environment and try to learn about it. That'll be tomorrow. Today, we're treating it this way because it allows us to generalize into a bunch of different kinds of games. So let's look at the pseudocode. So far, not so different. Yesterday, I kind of presented two different versions of this, one that was mutually recursive and one that had a dispatch like this. Now, instead of if the next agent is a max, get max value. If the next agent is a min, get min value. Max is the same, but if the next agent is a chance player, just call expected value. So let's zoom in on what that expected value is. Same as before, we are going to initialize at something, loop over all our children, and then accumulate them in some way. With min, it was take the minimum of all of them, but now we are going to take the expected value. And so that means, let's look at an example. It's a little easier. Most of the examples we're going to look at, just for simplicity, we're going to say it's uniform probability over all of the different actions they could take. If ever you see a chance node, one of these circles like this, and then there aren't probabilities written like this, we're saying that it's a uniform distribution over them. Usually that will also be written, but that's the typical example. In general, it's not necessarily the case. So while it's fresh, let's look at this example with an agent that is going to take this move with probability half, this move with probability third, and this move with probability 1/6. We want to take the weighted sum of all three of those utilities. So what's that going to be? Probability 1/2 times the utility if we take that action. So that's 4 plus 1/3 times 24. That's 8. 1/6 times negative 12. It's minus 2. Add it all together, and we get 10. So that's the process. Takes a little bit more work than max or min because we're actually doing some arithmetic. But same as before, we just propagate that value up the tree. And then if there were nodes up here, then we'd be recursing in exactly the way that we've already seen. Here's a bigger example. So, like I said, we don't have probabilities written on here. This is just going to be uniform distribution over the different actions. So let's work on propagating these values up the tree. When we're computing this value right here, we need the average of these three. So what is that? Just shout it out.
8.
8. Okay. And then what about right here? Heard a couple 4s. Yeah. And I'll slow down just a second. We got 8 by adding these together and dividing by 3. We got 4 by adding these together and divided by 3. And then we do the same thing here. What is that? 7. Right. And so now max is going to choose whichever maximizes its utility. That's 8. And so generally, when we're using this algorithm to play a game, we are modeling ourselves as the max player. And our move that we're trying to currently make is at the root. And so what this algorithm now would return when we're trying to act in the environment is the action to go that way. So yesterday, we saw a really clever trick with alpha-beta pruning, where we were able to basically guarantee that certain parts of the tree, no matter what outcome we found there, would not change the action that we take or the value at the root. Can we do that with Expectimax? We would really like to be able to do that because we saw that essentially doubled the depth that we were able to search. It's a dramatic improvement to the Minimax algorithm. But let's look at this. Let's think about this. So this is the same tree from before. If we're at this point and we have 8 in that node, and now we're trying to evaluate what's going to go right here. We've seen 2. Well, this could be 1,000,000, and this could be 3 trillion. And so no matter what, we can't really put an upper bound. Well, we cannot put an upper bound on what's going to go right here. And that means that no matter what we've already seen, we can potentially see something that will change the branch that we're going to follow to this one. Which means pruning does not work for Expectimax. You get this, a bunch of tangled nests. One quick aside that will come up on a couple of homework problems and discussion is you're going to see a lot of variants of Expectimax and Minimax where we combine these nodes in weird ways and give you nodes that behave in new ways. And you'll have to come up with rules about whether or not you can prune. Something important to know about Expectimax is if we have some bound on what the leaf utilities can be, say we know that all utilities are going to be less than or equal to 20. Now can we put a bound before searching this way on what's going to go in that chance node? Yeah, we can. We'd maximize it by putting 20s here, and then this would be 14. If that were the case, that's the max it could possibly be, so we know it's less than or equal to 14. If we wanted to actually prune, and say I told you that the utilities were, how can I do this? Less than or equal to 12. I don't know if that's going to work. Yeah, that'll work. Okay. Then that would still be the maximum again. And if we add all those, it doesn't work. Never mind. But yeah, unfortunately this is here, so it doesn't make sense for me to actually choose a small enough bound. But hopefully you see the point where there are situations where if we can guarantee by this reasoning, and this is the same reasoning that derived Markov's inequality in CS70, if you remember that. If we get a bound that says that this is less than, nope, it says this is less than or equal to 8, or better yet, something smaller than that, then we don't need to keep searching. We are able to prune in that case. There's an example of a variant of the game, some additional constraints that allow you to actually prune the tree. Any questions about that? Okay. So of course, same as yesterday, to actually search from our current position all the way to the end of the game along every single branch is completely intractable. That's the same as exhaustive DFS, where we're doing the branching factor raised to the depth of the tree, enormous. 35 to the 100 for chess, just way too big. So we can't do that, and the solution is the same as it was yesterday. We need to cut off the depth at some point and estimate what the expected utility from that point is going to be. The expected value, rather. Because remember, a value is the maximum expected utility we can expect to get. So if this is the whole tree, and we could follow this branch and end up here, instead what our algorithm is going to do, if we're searching one ply, so Pac-Man moves, and then each of these two random ghosts moves, and then it's Pac-Man's turn again, rather than continuing to search and recursing, we stop, we've hit our depth limit base case, and we return our estimates of the utility. So one thing that's interesting about this is that since there's so much uncertainty and randomness in this that was not present yesterday, having a lot of error in your estimate for Expectimax tends to make a lot less of a difference in how well your algorithm performs. Because if you have less depth that you're going to, on the one hand, your evaluation function is not going to be as good an estimate of the true expected utility. But on the other hand, if you were to increase that depth, you incur a bunch of randomness and variance in your estimate just by going deeper into the tree, that while it is generally always going to be an improvement to dig deeper, it's not as much of a difference as it was with Minimax. So in order to be able to run this algorithm, we need to have probabilities. We need to know what the distribution is between these different actions that the random players might take. So where do these probabilities come from? This is another modeling decision. We've been running into a bunch of these in the course of last week and this week, and this is going to actually become a pretty big one, where part of the problem, if you're trying to solve a real-world problem, is taking what you want to happen in real life and phrasing it in a way that our algorithms can solve. Coming up with these probabilities is, in some sense, a subjective way of doing this, because there are a lot of right answers in the sense that this model of traffic, where I say quarter of the time no traffic, half the time medium traffic, quarter of the time a lot of traffic, this might be a fairly good model, but you might disagree with me. You might think it makes more sense to have a continuous model, or we measure it in number of cars and then try to have a distribution over that. There are a bunch of different ways to model it, and making the choice between how to do it comes down to really the same balance that we've seen a bunch of times already, which is the more fidelity your model has, the more accurately it models the real-world situation where you're trying to solve a problem, the more intractable the math becomes when you try to solve it. And so you can imagine if this were some continuous probability distribution, we'd be taking a bunch of integrals and things would become a lot more difficult, both for us to reason about and for our algorithms to compute. Which is why, for all of our examples, while you're still seeing all this stuff for the first few times, are going to look like this. Traffic, pretty much there are only 3 possible kinds of traffic, and they occur with really simple fractional probabilities. Right now, we're going to cover probability in a lot more detail, either next week or the week after. For now, there are 2 axioms about probability distributions that are super important. You probably remember this, but they always have to be non-negative. You can't have a negative probability. And the sum of all of the probabilities has to be equal to 1. In other words, one of these events must happen. And so if you sum up all of the distinct events, their probability must add up to certainty. Okay. Quick reminder on expectations. So the expected value of a function of a random variable, and in that previous slide, our random variable was what was the traffic. Let's look back at that, actually. The event whose outcome is unknown, what will the traffic be? So an expectation is the expected value of a function of a random variable. So in this example, how long to get to the airport? Our random variable is the unknown outcome, how much traffic there is. What function of that random variable are we concerned with for answering this question? Well, think about this. I'll go back to it. Oh, actually, here, I can pull those guys up. So those are the three outcomes. That's our random variable. If this happens, we can probably get to the airport pretty quickly. Maybe it's 20 minutes away with no traffic. If this happens, that slows us down a little bit. Maybe it takes 30 minutes. And if this happens, it's going to be a lot slower. Triple our time, 60 minutes, something like that. So the function here, our random variable, we'll call it t. That's the traffic, and there are three possible outcomes it can take on. And then we can call f of t time to get to airport. So if I fill those in, 20, 30, 60, then it's now pretty straightforward how to compute that weighted sum. It's going to be that probability, quarter, times the outcome of that function, or the function applied to that outcome, 20 minutes, 0.5 times 30, and 60 times 25. So that, after we add them together, becomes 35 minutes. So this is the kind of computation we're going to be doing over and over and over and over again until it becomes second nature. Maybe you've already had a class where you had to do that. So, and if that's the case, you're in pretty good shape for the probability we're doing in this part of the course. But you want to become really comfortable with this weighted sum expectation idea. And just as a terminology note, the whole point of this thing over here, random variable, that's t, and function of a random variable, that's depending on which of those outcomes we get, how long does it take us to get to the airport. When we're talking about expected values, we're talking about numbers, right? Numbers like how long it takes, not which of these traffic outcomes. Okay, so now the question. I posed this modeling problem where we need to determine if we're trying to solve Pac-Man. We don't know exactly how the ghosts are going to act, or maybe even we do, but it's complicated enough that we can't model it perfectly and still have the algorithms work well. So here are a bunch of different options, and what we do in this class tends to be one of these things. The model could be a simple uniform distribution, and that would be something like if you're playing a game like Solitaire, where you're going to draw cards from a deck, and the cards that you get are going to just be more or less completely random. I guess you can remember stuff and have evidence that influences probabilities later. But for your first draw, you're going to draw something from that deck, and it's completely random. And you can model that as the random player in this game. Or it could be sophisticated and require a lot of computation. Looking at Pac-Man, if we are just modeling the ghosts in that first way, where it's simply random, and they're just, you know, flip a coin, if heads go left, if tails go right, pretty simple. On the other hand, maybe we can observe what they're doing for a long time and notice that it's moving right every time it gets the chance, and so learn a probability of how likely it is to go right by watching it a lot. Or we can gather a lot of evidence if we make the Pac-Man game more complicated, and we will do this when we get into the BayesNet section, where now you have ghosts that you can't see, but you can hear them. So you know how far away they are roughly, but not in what direction. Then you have to do a lot more computation to figure out these probabilities that they're going to move in whatever direction. So in general, this is pretty hard. And for now, we're not going to make you do it, because we're trying to just learn about the algorithms at this step. And you should know that in the real world, the algorithm is only half the battle. You also have to come up with the model. But for now, we have this really helpful probability fairy. It's going to always tell us the probabilities of every outcome. And we can just take expectations to run Expectimax. So I want you to think about this. Informed probabilities. Let's say you know exactly what algorithm your opponent is running to determine what move to make. And that's a depth 2 minimax using the result 80% of the time and otherwise moving randomly. So now think about what search tree we should use. And remember, we're going to use Expectimax, but now those chance nodes, the probabilities, are defined in this way. 80% of the time, the result of a depth 2 minimax, and 20% of the time, a completely random move. So think about that for 30 seconds or so. Oh, I guess I already said that. But how do we figure out those probabilities? And feel free to talk to your neighbors. I encourage it.
So, changing your bets with Expectimax might actually be optimally much better off assuming that it's and if maybe a random while you're making the best move, then you have a chance to go ahead because of Max, even despite the Expectimax.
Okay, so let me get some ideas. Raise hands and go around the room, things we thought of. Even if you don't have a complete answer to it, things that you think we must have to do in order to figure out these probabilities of different moves. Yeah?
Why don't we just use min-max here? Because 80%, that's 20% of the time we're going to make a move that is completely random and might go against min-max exactly. We could, there's a very good chance that by just using min-max we could outvalue them over time.
Yeah, that's a good point. And actually, part of the there's another reason that we might just use minimax to do this than what you said, but I'll point out that that's not exactly optimal behavior for us. It's much easier computationally than trying to figure out these probabilities, but it's possible that that 20% random move they make could open up some opportunity for us, like that tree that I keep showing where you have 10s no matter what happens down one branch, and then a 9 and a 100 the other way. If there's a 20% probability that we could increase our utility by a factor of 10, that's worthwhile in the expectation. So at least in order to play perfectly optimally, we are going to have to account for those probabilities somehow. So any ideas about how to compute these? Yeah? Some sort of estimate of the utility, of our utility? Yeah, so we are going to have to depth limit in that way. And we are going to want to figure out for them what the respective values of each of their actions is going to be so that we know during that 80% of the time when they choose the better move, which one they'll take. But to actually figure out those values, we have to actually simulate what they're doing, right? So here's the thought bubble. We're imagining what's going on in that chance node. And in order to compute the probability, we have a separate depth minimax search going on over here, completely separate from our search tree over here. And there's going to be one of these in every chance node. That's what happens when you have to simulate your opponent in this way. And you can imagine it's going to get, yeah, example probabilities. But you can imagine that it would get a lot worse if your opponent thinks that you are playing randomly according to some similar policy, because they are simulating you, right? And so you would have to now, in here, do the exact same thing and bubble out again and have your simulation of your opponent's simulation of you to perfectly compute what they're going to do. It gets out of hand pretty quickly. Yeah, question? Yeah, so adding these nodes to the main tree is not going to work out quite so well, just because these are going to, it's getting messy. I'm going to clean that up a little bit. The result of this search doesn't actually change any of the utilities or values in the tree. It's only to compute this probability. And so our formalism of what an Expectimax tree is at this point is we already know those distributions. So this is a process of running Expectimax Search in this tree. Before we can even run Expectimax Search, we have to have a way to compute these probabilities. There's not a clear way to put this tree into here and have the results of that search feed into what probability is going into the tree. Another question.
In that thought model, it's a minimax that you're using to simulate and get the probabilities, right?
Yes.
Okay.
So to be clear, when I say simulate and get the probabilities, what's happening is we use this and we figure out what the opponent thinks their best move is. Now we say with probability 0.8, they'll take that best move. Maybe that's this one. And then with the other probability 0.2, it'll just be random between the two. And that's how we end up with this 0.1, 0.9 distribution. But again, if they're simulating you, kind of catastrophic. It's just you get this infinite regress, and you have to now terminate how many simulations you're going to go into. The exception to this is kind of at the limit, minimax, where if both of you are playing optimally, then the probabilities, so to speak, of certain moves are ones and zeros and nothing in between. And you can collapse this all into one tree. So let's move on past that. Modeling assumptions. So the decisions we have to make in order to build a model. We already talked about the probabilities in Expectimax. And we need to figure out what utilities to use. But a pretty significant one is it more reasonable to use Minimax or Expectimax Search to solve this problem? So let's talk about the dangers of optimism and pessimism. Dangerous optimism is assuming chance when the world is adversarial. This is what happens if you run Expectimax against a ghost that is actually chasing you. And you might be just walking along confidently thinking, oh, it's not very likely someone will jump out of that cave and grab me. But in reality, they're trying to get you. And so you'll be led to do dangerous things, and that's pretty bad for clear reasons. But we can also go too far in the other direction. And what does that look like? Assuming the worst case when it's not likely. We have an example of what Pac-Man does when we do this, a demo that I'll show in a minute, and it's pretty funny. But here's another example. Is that a vampire rabbit? Who knows? It could be. There are all sorts of possibilities. So we should probably run away from this rabbit. Something like that. Dangerous pessimism, assuming the entire world is out to get you, is not necessarily a great modeling choice. So let's see what that looks like in Pac-Man. Oops. Go back. Okay. So two possibilities, right? Pac-Man could be using Expectimax or Minimax, and the ghosts could be playing adversarially or randomly. So if the ghost is random, you can expect in all cases we'll do better against a random ghost than one that's actually trying to ruin us. Expectimax is going to be properly modeling how that ghost is going to move and be able to maximize expected utility play really well, win every game with a pretty high score. On the other hand of that, if the ghost is playing adversarially and Pac-Man is simulating that correctly and always knows what to do in order to counter what the ghost tries to do, we'll still do really well. And so we'll win all 5 games, but of course, since the ghost is trying to defend the pellet, it will take some more time to get there, and we'll get a lower score. Now what happens in the dangerous optimism case, when the ghost is trying to get us and we think it's going to move randomly, we don't do so well. That's essentially Pac-Man's just going to rush the dot, and then the ghost is going to step onto it. It'll look like Pac-Man's completely unaware that the ghost is even there. And the last square, which is when we have random ghost and minimax Pac-Man, the dangerous pessimism. Well, you can see that since it's a random ghost, it's still pretty easy to get to that dot because the ghost is not doing anything to try to defend it. So he wins every time, but it takes quite a bit more time to get there than if Pac-Man is aware of that randomness. So let's see all of these in action. This is the smart ghost and the smart, oh, right there. Smart ghost and smart Pac-Man. So what do we think is going to happen? Yeah, he's going to run away from the ghost, and the ghost is going to chase him. Oh, it's kind of slow. Sad. My computer's old. But there we go. He runs away and then ultimately makes it around to the dot. And you might be thinking, why didn't the ghost camp the dot? Well, he's not doing depth infinity search. You might be seeing just in the short term he can get closer to Pac-Man. That's what's going on there. But let's look at a smart ghost and Pac-Man running Expectimax. So assuming that the ghost is going to play randomly. Now what do we think will happen? Yeah, he'll rush the dot, and then the ghost will just get it. What's he doing? I don't know. So I guess, yeah, at that one step where he did move away, he decided it was high enough probability that the ghost would get him, that he'd run away, and then something changed, and he no longer thought that anymore. This is a random ghost and playing Minimax. And this one's my favorite, because what does a random ghost do? Just wander around randomly in the bottom corner of the screen. And what does an overly pessimistic Pac-Man do? He runs away. So it's going to hang out up there just a bit. Oh, wow, he looked out really early. A lot of times this demo goes on for 2 minutes because the ghost is just going around in the bottom corner. Let's see that again. That worked out too well for Pac-Man. I'm not happy with that. Pac-Man should know what he's doing wrong. Yeah, this is a bit more typical. Yeah, run away. Stay up there. He's kind of stuck. He doesn't want to come away from that wall because he thinks he'll get eaten the moment he's in that ghost sight. And eventually the ghost will randomly wander to where Pac-Man can get around him, but sometimes it takes a while. Oh, he did it. That's exciting. Okay. And then let's see the example of when Expectimax is appropriate. So now we have a random ghost and Pac-Man playing according to that assumption. Now remember, since this is actually random, it's totally possible that Pac-Man gets eaten if he takes a chance and it doesn't work out for him. But he's accounting for the probability of that, and so on expectation, he's going to do as well as he possibly can. And this is what typically happens. Just gets the dot, and the ghost goes the other way, or some random other direction. So probabilities, which algorithm to use, is are we dealing with something of adversarial nature or random? And then the utilities, which we'll talk about a bit later. But first, I want to take an aside to talk about other game types. So the two game types we've seen are Expectimax with max and min nodes, and Minimax with max and min nodes, and Expectimax with expect and max nodes. But there's no reason that we couldn't mix them all up. And this is Expectiminimax, kind of an unwieldy name, but now we have max players, min players, and chance players. A great example of a game that works this way is Backgammon. If you don't know what Backgammon is, basically you're taking turns racing against your opponent to get some pieces to the other side, but how much you get to move is determined based on the dice roll. So now you have yourself maximizing your score, your opponent minimizing your score, and random events interlaced between the two things. So, yeah, another thing to keep in mind is when you're rolling dice, and in Backgammon actually the not just the sum of the dice, but what the outcomes on the dice are, you end up with a pretty big branching factor at the expect level. So if you have 2 moves you can make, your opponent has 2 moves they can make, and then there are 36 outcomes of the dice, then the branching factor for one full ply is pretty big. And we end up not being able to search quite as deep as with other games. But it turns out that, like I mentioned before, not being able to go as deep when there's a lot of randomness doesn't end up hurting us quite as much. And Backgammon was the first game where we had an AI that was able to beat a human champion. That was TD Gammon, historically, and it only used depth 2 search, which means it only looked 2 moves ahead, right? And then used an estimate of the utilities from there, and that was able to beat the human champion Backgammon player. Pretty impressive. And here's another kind of game that we didn't talk about. That's Expectimax. Here's something where it's not zero-sum. And this doesn't necessarily have to have more than 2 players. The same thing generalizes to 2 players or arbitrarily many players. But we like to use examples with 3 players because it allows for some interesting behavior. So now instead of one number that one player is trying to maximize and the other is trying to minimize, everyone has some separate utility function. Remember we saw that pile of gems that were different colors and the different agents were going for different colors. They weren't necessarily exactly competing against each other. And we keep track of this by now, instead of having a function that gives us the leaf utilities as one number, one real number, we have a tuple of the utility of this node for each respective player. And the algorithm is pretty simple. At all the green nodes, you take whichever of the children maximizes the green score, so that goes that way. At the blue nodes, you take whichever maximizes the blue score, and at the red nodes, maximize the red score. It's pretty interesting what can end up happening if you just use this algorithm, the kind of behaviors that can emerge. So it says right here that it can give rise to cooperation and competition dynamically. How does that actually happen? Well, here's the green guy and the blue guy working together. He's giving him hints. That could happen down here. Notice in the left half of the tree, green and blue's utilities are pretty close to each other. So as long as we're in this subtree, green and blue more or less want the same thing to happen. And so they tend to set each other up for good moves and cooperate. On the other hand, over here, green and blue could be working against each other. And that would happen if, as is the case, blue and green's utilities are almost opposite. Green is high when blue is low, and vice versa. So down this path of the tree, green and blue are going to be competing with each other, taking moves that hurt each other. And this all just happens from the computation, right? We're not explicitly encoding these behaviors of cooperation and competition. Just say, here are our utilities, maximize them, and then the way that they interact can become all sorts of complex things. So, big question. We kind of did this with probabilities already, but this might be something that's less familiar than modeling things with probabilities, which is, what are these numbers, these utilities, and where do they come from? It might be a little counterintuitive if you think about it for a moment, that we're able to attach a number to how much we like every single different outcome. How do we know that we could actually do that? Well, first let's talk about how we know that we need to be able to do that in order to model things well. And then we'll talk about how we can actually do it. Why should we ever have to average utilities? Why is minimax not always a good model? We saw some examples of that happening with Pac-Man, but in a lot of real-life reasoning, this can be a lot more dramatic than being scared of a bunny. Let's say we're trying to make a decision between all the different things we could do on a Friday night. Okay, your options are go to a movie, go to a party, stay in and work. Pretty simple, just give yourself those 3 options. And you want to try to figure out which of those things sounds like the best option. Well, if you go to a party, you might not meet anyone you like, you might not have a good time, and you might get hit by a meteor. All possibilities. So that doesn't seem so good. If you go to a movie, the movie might not be so great. You might fall asleep and miss some of it. There are all sorts of things that could happen, and you could get hit by a meteor. So that's not so great. And if you stay in and work, you might find out later that your friends went out and had fun and regret it, but also you might get hit by a meteor. And so the point is, if you're taking the minimum over all of the events that could happen when it's actually random, these catastrophically bad but infinitesimally unlikely events are going to completely dominate your calculations. And so either you have to simplify your model to just assume those can't possibly happen, or you have to take an average in this way. Principle of maximum expected utility, just a quick refresher. Remember that an expectation is just a weighted average. And we said this in the first lecture, and it's probably been said at least one lecture every time since then, because it's kind of the theme of the course, that once we have these utilities, we want the agent to be able to choose whatever action, whatever plan, whatever assignment in the CSP case, all sorts of different solution types, but out of all the things we could pick, whichever one is going to maximize the expectation of those utilities. So these are the questions we're going to answer. Where do the utilities come from? How do we know they even exist? How do we know that averaging even makes sense? And what if our behavior can't be described by utilities? We'll get into all of these in turn. Do you have a question?
If you average them, couldn't you have still gotten a whole lot of the same responses from the Expectimax problems in the Backgammon example? Like if you averaged getting eaten as with getting the dot, the pattern would still rush straight for the smart house.
If you average getting eaten with
getting the dot in 3 moves.
So, I mean, the way that's going to work out is, if you're assuming that the ghost is making random moves and it has to take a particular 3 moves to get to you, then that's 1/4 cubed is the probability that you'll get eaten if you try to get it. And then what's the utility of that? We'll say we lose 100 points if we get eaten. And then basically 1 minus that. All the rest of the probability is that the ghost doesn't get you. And if you eat the dot, maybe you get 10. So if I'm understanding your question correctly, this is the way that we average those utilities, is we say the probability of one event times that utility plus the probability of the other event times that utility. And if you work this out, this is going to end up being positive, which means that it's going to work out in the ghost's favor, in Pac-Man's favor to rush the dot if the ghost is moving randomly. And we computed that by taking this average. Let's move on for now. You can come ask me right after lecture. Okay. So what utilities to use? With Expectimax, all that matters is the order of the utilities. So over here, we have 40 is better than 0, and so we'll take 40. And then over here, sorry, that's a minimizer node. 0 is better than 40, so we'll take 0. And then 20 is better than 30, we'll take 20. And up here, 20. Over here, we've squared all of the utilities. But nothing changes all that much. In terms of which actions we choose, it's exactly the same. Max player will go that way, min player will go that way. Same over here. So this property is called insensitivity to monotonic transformations. For positive numbers, squaring is monotonic, which basically just means x greater than or equal to y if and only if x squared greater than or equal to y squared. Right? For positive numbers, this is the case. So if all of our utilities are positive, squaring them is not going to change the order of what these utilities are, and so they'll choose the same moves. However, erase all that for a moment. Oh, sad. I don't have an eraser, I just have to hit undo a bunch. If this is expectation, now what happens? The expectation here is 20, here it's 25, and so we take 25. Now when we square the utilities, this is come on. All right, 20, 25, 25, 800, this is 650, 800. So now not only did we end up with a pretty different root value after squaring all the utilities, that's okay, that happened with Minimax as well, but now what's happened is before this transformation, the choice of moves was for the max player to go right. Afterward, it went left. So something happened here. Basically what we have is, for Expectimax reasoning, it's not insensitive to monotonic transformations. So we need the magnitudes to be meaningful. When we squared this and made the 1600 much bigger, that actually had some bearing on how the behavior of the agents went. So now let's talk about coming up with utilities with meaningful magnitudes. So here's our general treatment of utilities. It's some function from outcomes, states of the world, to real numbers that describe an agent's preferences. So in the games that we've been talking about, they're usually pretty simple, straightforward. You want to win, and so you get 1 utility point for winning, and if you lose, you get -1. And then these algorithms we talked about, all this behavior of cooperation, competition, simulating the opponent, and responding to what you think they'll do, all this comes from just plug in these -1 and +1s at the bottom of this tree in the right place. But in a lot of cases, it's not so straightforward what those utilities should be, especially if we're modeling real-world problems, not games that are confined to who wins or loses. So let's do an example of where the numbers matter for something that has not quite an obvious answer. If we're trying to buy ice cream, and we want an agent that's going to figure out how much ice cream to buy for us, well, having an ice cream cone, that's kind of nice. You know, those taste kind of good, even on their own. So you might get some positive utility for that. Having an ice cream cone with a scoop of ice cream in it, now that's great, because I like ice cream. So that's going to be some other positive amount, and it's going to be greater than the utility of just having an ice cream cone. And then having 2 scoops, that's fantastic. It's twice as much ice cream, and you can get 2 flavors. So that's going to be even better. Now, let's talk about writing our algorithm to buy ice cream for us. We're trying to maximize how much ice cream we buy, and we can choose to buy a single scoop or a double scoop. If we get a single scoop, well, now we have a single scoop of ice cream and an ice cream cone, and we can eat it. That's great. But if we get a double scoop, that's a lot of ice cream piled high. There's a chance that we could end up dropping it. And then we're at 0 scoops of ice cream and just the cone. Very sad. So we're now having to take a chance if we buy the double ice cream cone, because we could get 2 scoops of ice cream, or we could drop everything and be really sad. So this is where it starts to matter. You can't just say what's better than what. We need to say how much better this is than this and this to be able to numerically compute and come up with an algorithm that's going to say which of those actions we can take. Here's our first step, preferences. So when I say preferences, we're just considering, the technical term here is prize. It means more or less the same thing as outcome as we used in previous slides, where it's the state of the world, and we're trying to define our preferences among a bunch of different outcomes. So if we say 1 ice cream scoop, 2 ice cream scoops, and 0, it's really easy to say our order of preference. We prefer 2 to 1, and we prefer 1 to 0. But the way that these numbers arise is when we start having lotteries like this. And lottery is another technical term. It just means
an event where you are either going to get one prize with some probability, you'll get A with probability P, or you'll get B with probability 1 minus P. Once we try to define preferences over these, we'll see that numbers start to kind of come out of it. Quick points of notation, you'll want to remember this because when we're doing math with these, you'll see these and we generally will not unpack that notation, so you want to become comfortable with that pretty quickly. Notice this looks like a greater than sign, and that's for a reason because it does define an ordering, but it's not a numerical greater than sign, right? It's not comparing real numbers, it's comparing two different events. I was using ice cream amounts, but it could also be getting a cat and getting a dog. If you like A, which is getting a cat more than getting a dog, then you would write this. And then the squiggly line, that means you're indifferent between the two. They're just as good to you. So we have a prize and a lottery. And a lottery looks suspiciously similar to those expectation nodes in our Expectimax tree. Okay, so rationality. We talked about rationality as taking the optimal actions to maximize our expected utility. We're going to go a little deeper into exactly what rationality means by talking about rational preferences. So now we're going to see a notion of there are preferences you can have such that it's actually impossible to behave rationally. So how can we avoid this? We want preferences that allow us to act rationally in the sense that we've seen. Well, there are some pretty reasonable constraints on how you order your preferences. This one is probably the most straightforward one, the axiom of transitivity. If you prefer A to B and you prefer B to C, then you must prefer A to C. What happens if that's not the case? If you have intransitive preferences? Well, you end up here. So let's call them apple, banana, carrot, ABC. If your robot has an apple and likes bananas more than apples, then someone could come along and say, hey, I'll give you this banana for your apple if you also give me 1 cent. And then he'll say, great, I like bananas more than apples. That's worth it to me. And then we've gone from here to here. Go away. Now he has banana. And you come along with a carrot and say, give me 1 cent and I'll trade my carrot for your banana. Worthwhile, great. And then the agent goes from this banana down to the carrot. And then you say, look, I have an apple. I'll trade my apple for your carrot. And the agent says, yes, that's worth 1 cent to me. And now he's back exactly where he started, but with 3 cents less. So the point is, if you violate this axiom of transitivity, then an adversarial agent could take advantage of you and essentially get whatever it wants out of you, more or less. That's also going to be the case for the other axioms of rationality, although the reason is not nearly as easy to see. But we are going to go through these and just hopefully agree that they sound sensible. So we saw transitivity already. What about orderability? That just says for two events A and B, either you prefer A or you prefer B or you're indifferent between them. It seems pretty harmless. We can assume that we can compare all events. Okay, so continuity. We're starting to get into the harder to grasp ones. This is consider 3 events, A, B, and C. B lies somewhere between A and C. Then there's some probability such that if you get A with probability P and C with probability 1 minus P, that'll be equal to B. You can kind of imagine if we're sticking this on a real number line, which is going to be our ultimate goal, get a real valued utility function. A and C are here. This means that B must lie somewhere between them on this line if the preferences are continuous in this sense. Substitutability just means if two events, 2 prizes, A and B, you're indifferent between them, then you're still indifferent if you plug them into lotteries. Seems pretty easy to believe. And then monotonicity, which says if you prefer A to B, then you prefer, in a lottery between A and B, to have higher probability of getting A. Another fairly harmless assumption. But now, what comes out of this? These are axioms, right? And so
any particular set of preferences does not have to obey these. But we have a theorem that says if you have a set of preferences over all prizes, over all world states, that obeys these axioms, then you are rational. And what we mean by that is actually just that you obey these axioms. But the mathematical consequence in this theorem is that it's possible to define a utility function so that your behavior of always choosing things you prefer can be modeled as maximizing some real valued utility function. And we're back to this MEU, maximize expected utility principle. That theorem is a pretty big deal in game theory economics. Happened quite a long time ago, 1931. I actually only recently learned that Ramsey had independently discovered it back then because it's called the VNM, von Neumann-Morgenstern utility theorem, since they discovered it 13 years later. Sad. But what it says is, choosing what you prefer can be modeled as maximizing some utility function. And they actually construct what this utility function is, u. So there exists this function u such that the utility of A is greater than or equal to the utility of B if and only if you prefer A to B with potential equality. And then what's really incredible about the way this works out is your utility of any lottery among a set of events is going to be equal to that expectation, the weighted sum of the utilities of all of the different prizes. So now we have a way to move from preferences over individual events to an actual real valued utility function that our algorithms that we've been looking at can work with. This u is now a way to actually assign those utilities to the bottom of the minimax tree or the Expectimax tree. And so this is kind of a key point in that modeling question. How do we take human preferences? What do we want this algorithm to do for us? If it's something more complicated than win a game, we need to do something like this, where we figure out what do we prefer over different outcomes and encode that into a utility function. So that transitions us into the next thing to talk about, human utilities. And I'll warn you in advance, this picture is going to help me. It's about to get a little morbid. Why is that? Well, okay, pause for a moment. Normalized utilities, if you just scale according to some factor all of the utilities up and down, then under random events, your utility is going to be preserved under linear transformations. So adding a constant to all the utilities or multiplying it by some positive constant. Of course, if you multiply it by a negative constant, all of your preferences flip. But positive constant and adding a constant, those aren't going to change it. Which means we can normalize all of our utilities, take the worst event possible and set that at 0, and take the best event possible and set that at 1, and work with a pretty manageable scale. How do we do that? Well, what's the worst event possible? You might disagree, depending on your philosophy, but a pretty good approximation to the worst thing that can possibly happen to a person is that they die. So our task now is to go around asking a bunch of people how much they don't want to die. And then we can kind of discover a scale for where our utilities lie. And there are two different ways this has been done. One is a micromort, and the unit micromort is the amount of utility that a human attaches to a 1/1,000,000th chance of death. Why would we want this? Well, when are we making decisions where we have to compare human death to something other than human death? You know, if you're saying, do we want 10 people to die or 5 people to die, that's an easy choice. But what if it's, do we want 10 people to die, or do we want to not recall our product and make $10 billion more? Now we need to start reasoning about how much we really care if people are going to die. And so this is elicited by essentially setting up a sliding scale where you say, let me jump forward to that actually. Oh no, that's on a later slide. We'll talk about how to elicit someone's micromort value a little bit later. Sorry for the spoiler.
Another way this has been quantified is quality-adjusted life years. And this is a bit more expressive than a micromort because now not only is it are you alive or dead, but it's a scale where we're trying to assess quality of life according to a bunch of different afflictions or life situations. And so you could say, if we have this normalized utility scale, where 0 is the worst possible thing, we could have death at 0, and then having a long, happy life at 1, and then maybe having a broken leg for a few years is at 0.8, something like that. And being blind but still living in a first world country is like 0.5. And then having malaria and dying at the age of 3 is like 0.1. Things like this, where it's now a scale where we're trying to assess all these things. And this is useful for the same kinds of calculations in economics, but another place this comes up a lot is trying to assess the value of different charitable interventions. You know, if you can go in and either cure someone's malaria or fix 3 people's blindness, how do you really compare what is better? We need a utility scale. And this is the one that tends to be most useful for trying to figure out people's preferences among those different things. So this is what I was saying before. If you have a positive constant and you scale it up and down, or another positive constant that's a bias, you add it up and down, all you're really doing is changing the scale of our utilities, but the order and the order of all lotteries is not going to change when you do this. And with deterministic prizes, yeah. So if there are only deterministic prizes and no lotteries whatsoever, then we don't actually need the numbers. That's what we saw with that tree where I squared everything. All that really matters is the order of everything. If you do anything that preserves order of your utilities, then what minimizing and maximizing people will do in the presence of deterministic choices can be fully specified just by the order over how you prefer outcomes. You don't have to address this magnitude issue. Okay, so utilities map states to real numbers. We want to figure out those numbers. So let's figure out how much a micromort's really worth. We're going to compare a prize A to a standard lottery LP between the best possible prize. So at utility 1, we have something like make $1 million. And at utility 0, the worst possible catastrophe, you die. So let's figure out with what probability would you choose just paying $30 to avoid making that choice? So we're actually going to use a slightly simplified model of this where instead of comparing the worst and best, we're going to say, how much money will you pay to avoid this lottery? With some probability, you're going to just leave and nothing's going to happen. And with some probability, instant death. Those are what could possibly happen if you choose this out of your 2 choices. And we want to figure out, you can either tweak the amount of money or the probability of these 2 outcomes. So for this example, we're doing probability. You could just as well try to figure out the amount of money that you would pay for if this P were fixed to something like 1/1,000,000th. And typically, for some reasonably small probability of death, like 1/1,000,000th, people are willing to pay $30 to avoid that. But if that gets any bigger, or sorry, if that gets any smaller, then people would rather not pay the $30 and do this. It's a little hard to reason about this because you think the fact that instant death is a possibility just makes it completely not worth it. But you have to remember that you're actually implicitly making these choices every day when you're deciding whether or not to drive in this rainy weather, or should I go swimming in that lake where there are alligators. Maybe you don't make that choice every day. I'm from Florida, so I do. And these kinds of things, this is implicitly something that we've learned how to do. And when we bring it to the forefront of our mind, it's difficult, but you can tweak the scales of these things to make it easier to elicit human preferences. Okay, so we talked about death. Let's talk about money. This is another scale that is familiar enough that a lot of people suggest it as a way to measure utilities of different outcomes. But there's one problem, which is that money does not behave as a utility function. What do I mean by that? Well, suppose you are a student, an undergraduate student in college, and you don't have very much money, and someone offers you a lottery between nothing happens and you make $1 million. We can simplify this a little bit. You're a student in college, and someone's just going to give you $1 million. We're not even making choices. We're just trying to say, how good is this? That's great. That's amazing. I really want $1 million. But if I already have $1 million, and someone offers me $1 million, it's not really going to mean as much to me. Doubling my money, as opposed to completely changing my socioeconomic class, is going to be a big difference. And then if I have $1 billion, you offer me $1 million, I say, no, I don't want it. Take it back. I don't need that. So it doesn't work out quite so clearly. There's not some exact utility to acquiring $1 million. And in fact, if we try to assign utilities, so now we have a utility scale and a monetary scale. So we're trying to determine between a lottery of getting this much money or this much money and a guarantee of getting this much money, which is somewhere in between. Where does that fit in? How does that all work? So we have this notion of expected monetary value, and I didn't put any numbers on the slide, and I want to right now. So $1,000 and $0. We could take a lottery between those two things, and be simple. We'll say just with probability half you get the 1,000, and probability half you get the 0. The expected monetary value, of course, is just $500. And this utility calculation right here, you'll notice, is subtly different than what's up here. And why is that? Well, we call the utility function right here. So depending on how that utility function behaves, what numbers come out of that, it might be the case that we order things differently when we're measuring the utility over just how many dollars. And it turns out that for most humans, that is the case. You behave differently. Most people would prefer having a guarantee of $500 to having this lottery. And in fact, you can lower that number a bit, 450, something like that, and still most people would prefer the guarantee of this to this. So the utility of the lottery tends to be less than the utility of its expected monetary value. The word for this is probably something you've heard before, the phrase rather, risk averse, right? We prefer the certainty of some lesser outcome to the chance of something great, but also the chance of something terrible. Well, something not so great. $0 isn't the worst thing that can happen to you. Yeah?
Well, why do people of every economic class buy Mega Millions? You got a tiny chance of winning. Like 1 in...
Great question. So why do people play the lottery? Right?
You're almost guaranteed to lose.
Yeah. So this is something we'll get at actually the last slide. Not exactly this point, but human utilities are complicated. And when you buy a lottery ticket, most people are not just blindly trying to maximize the amount of money they have. There's some utility you get from just the excitement of playing the game. And so to truly model the utility of a lottery game like that, you lose and you make $0, or you win and you make some billions number of dollars. And in both cases, you get some small utility bonus just for playing and getting to imagine what's going to happen if you get to win. And so when we try to really accurately model the way humans make decisions, these functions get really complicated. There's a lot of work on that in cognitive science disciplines, but that's just one of many ways that human decisions can be seen to be rational if you account for all sorts of other things that are going on in a person's head when they make these decisions. Great question. And one other interesting point, they're not always risk averse. If you're really deep in debt, people tend to be risk prone. Because it's like, how bad could it really be? Can it get worse than this? And then you're willing to take a bet where if you're already at negative $1 million and someone says with probability half you'll get $2 million, and with probability half you'll get negative $10 million, you might take it. I mean, that's kind of crazy. That's really negative expected value, expected monetary value, but it's kind of leveled off in the other direction, where how much worse can it get? You're already so far in the hole that being $10 million more in debt probably doesn't change your quality of life all that much. So this is what that curve tends to look like. This is, again, elicited by trying to make humans make decisions between various lotteries and guaranteed things. And so you end up with a curve that at 0 is 0. We kind of fix it there, but people tend to treat it that way as well. And then as you go up, it kind of grows logarithmically, where every time your money multiplies by a certain amount, you increase your quality of life by a constant amount. And then going in the other direction, that trend continues until it actually flattens out and starts to level in the other direction. And that's that risk-prone when you get to really negative utilities. So let's look at a couple examples. Insurance. This is that lottery I was just talking about. You can either get $1,000 with probability half or 0 with probability half. The expected monetary value is $500. What is its certainty equivalent? So this is another economics term, certainty equivalent. It's what amount of money would someone take with certainty that would make them indifferent between that and this. So if you're offered more than the certainty equivalent and you can just take that without any randomness, you would prefer that to the lottery. And if you're offered less, you would prefer the lottery. So who would trade this lottery for the certainty of getting $10? Let's raise hands. $10. Anyone? Going once? Going twice? Okay. What about $900? Raise your hand if you would prefer to get $900 than to play this game. I'm surprised that's not all of you, but okay. It's most of you. That's good. $500. This is where we're starting to get into the murky areas. Still most of you. Looks like almost the same group of you. $400. Who would prefer to get $400 to playing that game? I'm seeing about half. Okay. Typically, people prefer $400 to taking this lottery. And we kind of see that. I think if you were to condition votes on people who were raising their hands at all in the first place, then we got most people still preferred $400. And that's good. That's pretty normal. So there's an interesting difference here, right? We have two numbers, 500 and 400. The fact that those aren't the same has some meaning. It's called the insurance premium. That's how much a person is willing to pay in order to get the certainty and eliminate that randomness, is $100. If everyone were risk neutral, we wouldn't need insurance, right? We'd be indifferent between the possibility of dying and the possibility of making $1 billion and whatever lies at the middle of that. But that's generally not the way people behave. That's why people buy insurance. And it's a win-win. You might think this sounds like the companies are taking advantage of people because the expected amount of money they're making is just going down. But in fact, we're not really interested in measuring the expected amount of money. We want the expected utility. And when you apply this utility function to all of these, it works out such that both people prefer the outcome they got. This is an actual interesting real-world example of a game between the insurance buyer and the insurance provider that is not zero-sum. And they cooperate in this case. Because as the consumer, you are happy to pay $100 to lose that randomness. And as the provider, you're making a ton of these lotteries, and so you start to benefit from the law of large numbers. The amount of money you make converges to the probability distribution here, and you start getting roughly equal to the expectation. And so everyone is gaining. And this is that last slide about human rationality that I was talking about. It's pretty interesting what happens here. So let's compare two lotteries. With probability 0.8, you get $4,000, and 0.2, you get nothing. And then the other one is certainty of $3,000. Let's get hands for A. Raise your hand if you prefer A. Oh, no one. Okay. What about B? Good. Yeah, almost everyone. And that's really typical. Almost everyone prefers B here. Even though the expected value here is 3,200, slightly higher. Let's look at a couple more lotteries, C and D. 0.2, you get 4K. 0.8, you get nothing. 0.25, you get 3K, and 0.75, you get nothing. This might be a little harder. Think about it for like 10 seconds. Actually, I'm going to give you like 3 seconds. All right, who prefers C? Almost everyone. Who prefers D? A couple people. Okay, so yeah, this is also not as straightforward a choice, but generally everyone chooses C. Most people prefer B to A, C to D. But if we fix the utility of $0 to be 0, which is generally a pretty reasonable scaling choice, then this is what this works out to be. B is preferable to A, means that the utility of $3,000 is greater than 0.8 times the utility of 4,000. And C is greater than D. Well, we can just multiply these by 4, and then you get 0.8 times 4K is greater than 1 times 3K. What does that mean? Well, here, oh no, come back. This is a contradiction, right? Utility of 3K is greater than the other one, and also the opposite is true. So somehow we messed something up here. And this is another place where, with a simple enough model like this, where we're just talking about a utility is a function of money, humans appear to be irrational. And you might argue after seeing this that this doesn't really fix it. They are still irrational. But in this experiment, this example by LA in 1953, the reasoning they came up with for why this was happening depends on this particular outcome. What's happening? Well, you could have chosen to get $3,000. And so for most people, the utility of this outcome is worse than 0. There's some utility that comes from frustration, embarrassment, and stupidity, the feeling that you get for choosing that lottery when you could have had it all, or at least almost all of it. And so taking a risk where you shouldn't have. And so for a lot of humans, that has negative utility. And here it is again. If you try to account for all of these things and have a really accurate model, it gets so complicated that the math gets difficult. And so it's complicated, and we need to figure out some middle ground for what accuracy to model all of this in. Okay, thank you.